Keeper 8.3, volume of solids with known cross sections. Okay, so we have two kind of important formulas. The first one is when we're taking cross sections perpendicular to the x-axis. Basically, when we do it perpendicular to the x-axis, our formula is going to be in terms of dx. And if I'm doing it perpendicular to the y-axis, our formula is going to be in terms of dy. So it just depends on what axis they're asking you to do it in respect to. If they're saying do it, perpendicular to the x-axis, use the first formula. Perpendicular to the y-axis, use the second formula. All right, so our steps for finding the volume. First, you want to draw the base. Then you want to draw a representative cross-section, like what would a cross-section actually look like if I was to slice it, like I'm slicing a loaf of bread. Find the area of the cross-section, and then you want to set up the integral with your bounds, and then you're going to integrate, which will give you your volume. All right, some important formulas you need to know. We have the area of a square. You guys should all know that's base squared. I know a lot of people say length times width or base times height, but if it's a square, the base and the height or the length and the width are the same, so we can just say base squared. If it's a semicircle, and we're doing it in terms of the base, so in terms of the entire base of a semicircle, our formula would be 1/2 pi times base over 2 squared, or simplified out, I can write that as pi over 8 base squared. Next, we have the area of rectangle, which is area equals base times height. In these problems, they have to tell you some relationship between the base and the height. They can't just say, base and height equals whatever. Everything in these problems have to be in terms of base. So they have to tell you some relationship between base and height to actually work it out with a rectangle. And then we have our isosceles right triangle with a leg on the base. That's 1/2 base squared. But they could switch it up and they could give you an isosceles right triangle with the base as the hypotenuse. And if that's the case, you're going to do area equals 1/4 base squared. All right, so for the first example, it says find the volume of the solid whose base is the region that's bounded by y equals square root of x equals 9, and the x-axis. The bases of the cross sections are perpendicular to the x-axis. So that's important because I know now I'm going to use my first formula. And they want us to do cross sections in this particular example that are squares. So I'm going to start by drawing my region. So I have the square root graph, and I stopped it at x equals 9 because that was the boundary they told us. And the x-axis, which is, you can see it lightly, but it's this green line running along the x-axis. So I'm going to shade my region. Once I shade that region, I want to figure out what my cross section is actually going to be. And so basically what I'm doing, I'm thinking about this almost like in 3D, and I'm thinking about how I'm going to slice it. Like I said, almost like it's a loaf of bread or something like that. You want to slice it. And the idea is that we're taking really, really tiny slices, almost like a Riemann sum, but we're trying to take as small slices as possible to get the most accurate answer. And so I'm going to slice it right down from top to bottom. Notice I said from top to bottom, right? Just like in the area problems, we always do top to bottom, right, left, right minus left. This one I'm going top to bottom since I want to be perpendicular to the x-axis, and that's my base. Now understand that's not just any old base, it's actually a square, right? It's kind of popping out the paper, and it's a square with that base on the axis. So like this base right here that I'm highlighting is the same as this base in the picture. All right, so I'm thinking some of y'all probably like, what the heck is she talking about? So I'm going to try to show you guys in 3 dimensions what it actually looks like. And so this is kind of what we're doing. We have some 3D shape, and we're slicing it up. We're slicing squares into this three-dimensional shape. All right, so the way we calculate our actual volume is we're going to do the integral from 0 to 9. And again, we're using x values as our bounds on the integral because we're perpendicular to the x-axis. So we're going integral from 0 to 9 of the function squared, or of the base squared. And in this case, our base is the square root of x because the top is root x and the bottom is 0. All right, so it'd be like root x minus 0, top minus bottom. So we have root x squared. All right, now when I clean this up, I'm going to have the integral from 0 to 9 of x dx, and then I'm going to integrate that to have x squared over 2 from 0 to 9. Plugging in my bounds, I get 9 squared over 2 minus 0 squared over 2, which is simply 81 over 2. All right, so next example, it says find the volume of the solid whose base is bounded by y equals square root of x equals 9, x-axis, so same exact example, except for this time we're going to be using semicircles. So instead of squares, we're going to go semicircles, but we're still perpendicular to the x-axis. So again, I'm going to graph out my region. I'm going to draw my little base, understanding that my base actually looks like a semicircle right now. And again, it is three-dimensional, so it almost looks like a piece of corn, right? Like a little curved out half of a corn or something like that. All right, so now I want to do my integral. Now remember, we're doing semicircles, so our formula for semicircle is pi over 8 times your base squared. Again, our base in this example is going to be square root of x. Again, that's because we're doing the top, which is square root of x, minus the bottom, which is 0. So we get square root of x as our base, and then we have to square it to satisfy our area formula. All right, so simplifying that, I get pi over 8 times the integral from 0 to 9 of x dx. And then integrating that, I get pi over 8 times x squared over 2 from 9 to 0, which would be pi over 8 times 9 squared over 2 minus 0 squared over 2, which is 81 pi over 6. All right, so again, same exact example. This time, though, we're going to do it with a rectangle with a height equal to 1/2 the base. Remember, I told you for rectangles, they have to tell you the relationship between height and base. All right, so just like before, I'm going to draw my example out, and I showed you kind of like the 3D shape, but like imagine us drawing the full example. It's going to be the same graph that we've seen from the previous examples, but this is what it would look in 3D with the rectangles popping out of the shape. All right, so we're going to do the integral from 0 to 9 just like we did before. And remember, your formula for a rectangle is base times height. Now, we know that the height is 1/2 the base, and the base is root x. So we'd have 1/2 root x times root x. Simplifying that, I'd have 1/2 from 0 to 9 of x dx, which would be 1/2 of x squared over 2 when I integrate from 0 to 9. And then plugging in those bounds, I'm going to end up with 81 over 4. All right, so same example again. Notice I just keep using the same example. I'm just trying to show you the differences in how our answers come out, or versus how our pictures look versus what formulas we use, even though we're using the same exact example. All right, so this time we're doing it with isosceles right triangles with a leg on the base. So I kind of gave you a three-dimensional view of what that would look like. And so remember, our formula for isosceles right triangles with the leg as its base is 1/2 times your base squared. Again, in this problem, our base is simply root x. And so cleaning that up, I get 1/2 from 0 to 9 of x dx. We just solved this on the last example, so just working it all the way out, I'm going to end up with 81 over 4. All right, so this next example is a little bit different. It says find the volume of the solid whose base is the region bounded by y equals x squared and y equals 9. Bases of cross sections are perpendicular to the y-axis, and we want to use cross sections of squares. All right, so I'm going to start by graphing my region. So I have y equals x squared, which is a parabola, and y equals 9, which is the horizontal line at 9. And basically all I want to do is I want to draw my base in, but this time it's going to be perpendicular to the y-axis. And so you can see I drew my little base. Now imagine little squares stacked up out of this. Now, because I'm perpendicular to the y-axis, everything this time has to be in terms of y. So like my function or my base has to be in terms of y, and my bounds have to be in terms of y. All right, so the first thing I'm going to do is I'm going to take my equation y equals x squared, and I'm going to solve that for x. So I get x equals the square root of y. Now understand x equals the square root of y is just really this piece right here. The left-hand side of this is actually x equals negative square root of y, like we would have a plus or minus situation. So because we have two pieces, like a right piece and a left piece, when I do my integral, I want to account for that square root of y 2 times, once for the right and once for the left. Or you can think about it as right minus left, like square root of y minus a negative square root of y. That's going to be 2 square root of y. And so our base is 2 square root of y squared because we're doing squares. And so when I square this out, I get the integral 0 to 9 of 4y. I pulled the 4 outside of the function dy. Again, please understand everything, even my bounds, are in terms of y because we're perpendicular to the y-axis. Alright, so I'm going to integrate this. I get y times y squared over 2 from 0 to 9. Plug in my bounds and simplify. I end up with a final answer of 162. Okay, for this example, a solid has a circular base of radius 2 in the xy plane. Cross sections perpendicular to the x-axis are in shape of isosceles right triangles with the hypotenuse as the base of the solid. Find the volume of the solid. So the very first thing I'm going to do is I got to start with some type of formula. So the very first sentence, it says that we have a circular base of radius 2. And so I know from, again, pre-calculus conics that my equation for the circle would be something like x squared plus y squared equals 4. And I drew it out here for you at the bottom. Now understand that we're stacking these isosceles triangles so that their hypotenuse is on the base, so the longer side is covering the base of this figure. Now, because we're perpendicular to the x-axis, I'm going to solve for y, so I get an equation in terms of x. So I subtract x on both sides, and then I square root, and I get y equals plus or minus square root of 4 minus x squared. All right, so looking at that like visually, square root of 4 minus x squared is like the top part of the circle, and then negative square root of 4 minus x squared is the bottom of the circle, and the base is extending from the top to the bottom, so top minus bottom. All right, so when I go to integrate this, remember that we're using the formula for a right triangle with hypotenuse on the base, which is 1/4 the base squared. All right, so we have integral of 1/4, or you can pull the 1/4 out front, from -2 to 2. Notice that I use x bounds because we're perpendicular to the x-axis and basically all you want to do is take your top minus your bottom. And in this case, our top is root 4 minus x squared, and our bottom is negative root 4 minus x squared. So I'm going to end up with 2 root 4 minus x squared squared. Now simplifying that out, I'm going to get the integral from -2 to 2 of 4 minus x squared. Integrating that, I'm going to get 4x minus x cubed over 3 from -2 to 2, and then plugging that in and simplifying, you should get a final answer of 32 over 3. All right, so for our last example, it says find the volume of the solid whose base is the region bounded between the curves y equals x and y equals x squared, and whose cross sections are perpendicular to the x-axis are squares. So for this problem, we need to graph it out. So I'm going to graph out x squared, and I'm going to graph out x. And basically, when I graph this out, I'm going to draw my base, and I'm notice my base is going from top to bottom. Again, because I'm perpendicular to the x-axis. And so when I do my problem, just like when we did area, we want to compute top minus bottom to figure out what our base is. And so we're going to integrate from 0 to 1 because that's the bounds from left to right on the x-axis of top, which was x, that's my linear function, minus bottom, which was x squared squared. And again, we're squaring it because we're doing our cross sections are squares. All right, so working this out, I'm going to go ahead and distribute that squared out. So I have x squared minus 2x cubed plus x to the 4th from 0 to 1. And then integrating that, I get x cubed over 3 minus x to the 4th over 2 plus x to the 5th over 5 from 0 to 1. Plugging in my bounds, and again, I don't really have to worry about that bottom bound of 0 because that's going to give me 0. I get 1/3 minus 1/2 plus 1/5, which is 1 over 30.